We're now prepared to use algebra to build models of real life situations. And we're going to start out with what are probably the most familiar models we have available to us, linear models. So if we have two variables, what does it mean to say that they're linearly related? Well, notice here we have a linear expression describing this function f. We're going to say that f is a linear function, and we're going to identify some of its characteristics. So if f of x is 5x plus 3, we're going to start with just some values of x, and we're going to find the corresponding values of f of x and call those y. So when x is negative 2, we can take f of negative 2, and that's going to be 5 plus 3 times negative 2. Just putting that into a calculator, it comes out to be negative 1. So when x is negative 2, f of x is negative 1. Next, when x is negative 1, we can take f of negative 1. That's going to be 5 plus 3 times negative 1. And again, throwing that into the calculator, we get that that's 2. So input negative 2 gives output negative 1. Input negative 1 gives output 2. When x is 0, we can take f of 0, which is going to be 5 plus 3 times 0, which works out to 5. When x is 1, we can take f of 1. That's going to be 5 plus 3 times 1, which, according to our calculator, comes out to 8. Finally, when x is 2, we can take f of 2. That'll be 5 plus 3 times 2, which comes out to 11. Okay, so the way that we came up with that table was just by plugging into our function. But now I think if we take a minute and look at the table, we're going to see a pattern. Every time we go down a row in this table, we're adding 1 to the value of x. But then, looking at the y values, every time we go down a row, we're not adding 1, but we're adding 3. Right? Negative 1 plus 3 is 2. 2 plus 3 is 5. 5 plus 3 is 8. 8 plus 3 is 11. So each time we go down a row in a table, we see that each time x increases by 1, each time x increases by 1, we see y increases by 3. In other words, we can describe this as a constant change in x by 1 each time in this case, producing a constant change in y. So what we see is that these are all the same number, in this case all 1s. These are also all the same number, in this case all 3s. Whenever we see that pattern, we're also going to notice a pattern in the graph. So I'm going to draw all of these pairs on the graph, and we'll see what pattern that makes. When x is negative 2, y is negative 1. That's this point. When x is negative 1, y is 2. That's this point. When x is 0, y is 5. That's this point. When x is 1, y is 8. that's this point. When x is 2, y is 11, that's this point. And what we see here is that all of these points are lined up along the same straight line. We can draw the line that goes through all of those points. And that line is the graph of our equation. So what did we see in this example? We saw that the equation for our function is linear. And we saw that the graph of our function is a straight line. And what we're going to do now is to associate that function type, a linear expression for the function, and that graph, a straight line, with that pattern that we see in the table. Here's an example that's associated with a story. Alice's car gets 25 miles to the gallon on the highway, meaning that every time she drives 25 miles, she uses 1 gallon of gas. She begins a trip with 13 gallons of gas in her tank. And so what we want to do first, just to get a sense of what's happening here, is to make a table of values showing a relationship between the distance that she's driven and the amount of gas she has left. Now this says every time she drives 25 miles, so that means every time she adds an extra 25 miles driven, she uses 1 gallon of gas. So every time she drives another 25 miles, she's going to subtract 1 gallon of gas. So when she's driven 25 miles, she has 12 gallons of gas left. Drive another 25, so now she's driven 50 miles. She has 11 gallons of gas left. Another 25, so she's driven 75 miles. She has 10 gallons of gas left. Another 25 when she's driven 100 miles. She has 9 gallons of gas left. So again, we can look at the graph of this relationship just based on the table, and we're going to notice a familiar pattern. Just putting a copy of that table next to our axes so we can see them at the same time. When d is 0, g is 13. So I'm finding the 0 on the d-axis. 13 on the g-axis is going to be halfway between 12 and 14. So this is the point 0, 13. When d is 25, g is 12. Paying attention to the labels on the d-axis now, which count by 25s. This is the point 25, 12. And then we have 50, 11, 75, 10, and 100, 9. And we spot that once again, those points are all lined up along a straight line. So we can draw that straight line, and we get a graph that shows the relationship between the distance that she's driven and how much gas she has. Now, I claim that the equation g of d equals negative 1/25 d plus 13 describes this relationship. So we'll see how we would get that equation in a little bit. Right now, I'm just claiming that that equation is correct. And we're going to check by showing that that matches the values in our table. So when x is 0, we'll take g of 0 equals negative 1/25 times 0 plus 13. And putting that into a calculator, we get 13. When d is 25, we'll take g of 25, which is negative 1/25 times 25 plus 13, which does indeed work out to 12. When d is 50, we'll take g of 50, which will be negative 1/25 times 50 plus 13, which will indeed work out to 11. G of 75 is negative 1/25 times 75 plus 13, which is 10. And G of 100 is going to be negative 1/25 times 100 plus 13, which is indeed 9. So, plugging into that function, we do indeed get the values of g of d that we were expecting. So that function really does fit the table that we have. Now let's think about where we could find the negative 1/25 and the 13. Negative 1/25, notice every time we went down a row, y decreased by 1, x increased by 25. The negative 1/25 is just the fraction, the change in the output, so the change in our output in this case is g, divided by the change in the input. So in this case, the change in d. We can also find the 13 in that table. The 13 was the starting value of g. That is, it was the value of g when d was 0. Keeping track of where we see these is going to be helpful when we get to the point of writing down an equation based on a story or a table like this. So again, the function has a linear expression. The graph is a straight line. In the table, a constant change in the input produced a constant change in the output. This is what we call a linear function, and when it's applied in real life, a linear model. So a function now is linear. We've defined a linear expression and a linear equation. A function is linear if a constant change in x, that is the input variable, produces a constant change in y, that is the output variable. When we have a linear function used to describe a real-life situation, we say that it's a linear model. A function we're using to describe something in real life is a model. If we have a story about a real-life situation that's going to call for a linear model, that situation shows a constant rate of change. A constant rate of change in a story is what's going to alert us that a linear model is what we want.